So, so what I'll talk about today is the use of computational toxicology models, and I'll start by with a few slides discussing why this area has become or is becoming increasingly important in various applied areas of chemical toxicity assessment, including drug toxicity, chemical toxicity, medical device toxicity, etc. I'll talk about some of the key methods and best practices for model development for in silico to in vitro to in vivo extrapolation, allude to how not to build models, including modern strategies for deep learning and AI, show one example application, and then we'll talk about where we are in general. So let me start with how the modern chemical toxicity modeling had started and what really precipitated the current major developments in this. And that takes us back 15 years to a future of toxicity testing defining documents and policies spearheaded by the national academies that created a program called TOX21 as a way of transforming chemical toxicity testing away from animal testing and more toward a mechanistic explanation of chemical toxicity and development of tools and protocols that rely on in vitro testing and mechanistic modeling and interpretation of chemical toxicity. And what's behind it is that historically, testing of chemicals has been accomplished in recognized and accepted by the regulator animal tests, which inadvertently dealt with executing a lot of animals and not necessarily building predictions that would extrapolate to humans. And this analysis has been done without a really deep understanding of why chemicals cause certain types of toxicity. And so TOX21 and TOXCAST program that followed had suggested that we should study chemicals that first with known in vivo toxicity and try to figure out what makes them toxic by running hundreds of in vitro testing protocols, really hunting for possible mechanisms that could explain toxicity, and then employ computational modeling. And you could see the word bioinformatics, but not cheminformatics. And that's one of the first points I'm going to make. Use computational tools to build models that could explain in vivo toxicity based on in vitro data and models of in vitro data. So that started a large number of tests run on thousands of chemicals at EPA and FDA and individual universities, companies generating a lot of data. And on top of push for better science, in recent years, it also, and it's really recent years, meaning this year, there is growing pressure from regulatory agencies to develop alternative toxicity testing methods, as these quotes from both FDA and EPA indicate, including a pretty strong statement from US EPA in 2019 to eliminate all mammal chemical testing for toxicity by the year of 2035. So that's where we are. And reflecting these trends, there are also recent estimates as to how global computational toxicology solutions market, as well as in vitro toxicology testing markets, and the two really come together because the objective of in vitro toxicology is to extrapolate to humans, and so it's unavoidable to employ computational methods to analyze this data. So that's what the trends are. So it's really for computational chemists, for cheminformaticians, it's really an opportune time to study toxicology and learn how to develop better models that could forecast in vivo safety of chemical agents across, again, as I mentioned, any industry that manufactures and sells chemicals. So let's talk about historical methodologies, the strengths and weaknesses that have been developed to understand and learn how to predict chemical toxicity from chemical structure. And there are really two major historical trends. The one on top on the slide is so-called chemical categories and read-across methodology, which is a relatively simple chemical similarity-based method, with the key aspect of this method being extraction of so-called structural alerts or chemical toxicity alerts. I'll talk a little bit more about it, which are chemical fragments presumed to be associated with a specific type of chemical toxicity. And of course, in parallel with that, statistical methods of quantitative structure activity relationships, building binary classification, real value models, directly computing toxicity values or toxicity categories from chemical structures have been developed. And historically, regulatory agencies have been given much higher weight and much higher recognition to the chemical categories and read-across method for a simple reason of transparency and mechanistic interpretability, because it's very easy to see why a chemical is toxic. All you really need to do is to look up existing structural alerts of toxicity and make an assumption that the chemical is toxic. So just to dwell on it a little bit more, this is an example of how structural alerts are identified and how this concept proliferates into fields of drug discovery or REACH, which is a regulation of chemical products tested for toxicity. So structural alerts are molecular patterns that are associated with specific types of toxicity or adverse effects, directly or indirectly, including undergoing metabolic activation in vivo. So in vivo. So this is the definition. And there have been and continue to exist multiple tools that all belong to this chemical read-across category, where toxicity assessment or toxicity prediction is made by comparing the structure of a chemical in question to known chemicals showing the same type of toxicity. One of the most popular tools, and it's open access tool that has been supported in Europe by OECD and distributed around the world, the so-called OECD QSR toolbox, which is very actively used by regulators to fill in gaps in the current knowledge. And as you could see from this diagram, the implementation of this method is based on grouping of chemicals into chemical categories, and then again presuming that in the read-across approach, that a new chemical of interest has the particular expected toxicity because of its similarity with other chemicals of the same chemical category. In QSR methods, of course, there is no mechanistic assumption up front. There is a hypothesis that one could build statistical models correlating chemical descriptor matrix with the target property and expect to see a strong correlation between actual and predicted biological activity or toxicity. And the practical utility of this black box methods, again, no pragmatic assumption as to why chemicals cause this or that type of toxicity, is to create models that could procure external databases of unlimited size, really, of chemicals and make a prediction as to whether a chemical is expected to be toxic or non-toxic. But the prediction is made solely based on statistical models without any implied mechanism of action. On occasion, one could analyze the results of the models in terms of descriptor significance and try to make an assumption as to which chemical descriptors, especially if they can be interpreted, could be behind the specific action of a chemical compound. So let me address the comparison between these two approaches. And let me say upfront that based on years of research in my group and other groups, what I will share with you is a concern about chemical toxicity alerts and explain why we have this concern, and basically then talk about how the advantages of read-across and statistical modeling of chemical toxicity could be addressed in methodologies and tools that integrate the best components of both methods. But let me start with analysis of chemical alert. And the word alert is chosen for a reason, because essentially it's a statement of a possible association. The word alert is much weaker than the word or term prediction. And therefore, it's rather safe to use this word, but what really we want to know is whether a chemical is safe or not. And so in all practical matters, we want not just a suggestion or hypothesis, but a strong validated assertion. And that's where chemical alerts and read-across really fail to deliver, because for chemical alerts, one could only make one statement. It's present in a chemical structure, or it's absent in a chemical structure. And typically, alerts are derived from a large collection of chemical structures that happen to have a particular chemical functional group. And so what I'm showing here are well-known, well-characterized cardiotoxicity alerts, specifically chemical fragments thought to be associated with hERG blockage. But if you look across these examples and across compounds that have been processed with these examples, what I compare here is the results of QS error prediction of molecules containing these alerts versus the assessment of toxicity for these molecules based on presence of alerts. And if you carefully look across, in every given case for two different chemical alerts, if chemical alert read-across strategy is used, a molecule is predicted as blocker. Whereas in QSAR, molecules are predicted as blocker or non-blocker, and there is much high agreement with the experiment between QSR-based prediction and alerts. And that really characterizes the limitations of alerts, because again, there are multiple compounds in which they are found, and compound is toxic, but there are also multiple compounds, and sometimes a lot of compounds that have this alert fragment but are non-toxic. So, for instance, initially, these alerts will probably derive from small data sets, but if you look at the modern collection of chemicals, about half of them have this alert and are blockers, and half of them have this alert and are non-blockers. And kind of the same is true in the second case. So that's an obvious limitation. And this limitation has been recognized. And so you could read in the description of one of the tools, toxicity, that is entirely based on read-across, that recognizing these limitations, the name was changed to chemical sensitization reactivity domain to reflect the fact that alerts provide grouping into reactivity mode, but do not predict skin sensitization potential. And reading this really caused me to think about how the statement can be interpreted and what's the utility of chemical alerts is if you can't really make any predictions or strong assertions. And so the sort of the finish with this part of the talk, the visual that I thought was associated with this particular observation is shown on the screen. And I imagine, I can't see anyone listening to me, but can imagine that you realize how confused one would be entering the park with this kind of signs at the end. So what can we do with it and about it, and what has been done? QSR models are black boxes, but they give more accurate prediction about chemical toxicity. Alerts report a possible association But unlike QSR models, are completely visible, interpretable to a chemist, interpretable to a toxicologist, and are much, much easier to implement. And so what can be done, recognizing the strengths and weaknesses of both methods? What I'm talking to you about now is a methodology that can unite and has united both of these concepts, and which allows really to make both prediction and interpretation of models. And in part, it relies on the aspect of statistical QSR modeling that is has been gaining more attention in pretty much throughout the entire the history of the field development, but a lot of emphasis in recent years with the development of really black box models such as deep learning as to how to build explainable statistical models correlating chemical structure and activity. And the strategy combines building statistical QSR models, interpreting these models in terms of significant chemical fragments, and using these models also to assess the significance of structural alerts derived solely from looking at the structure of toxic compounds without any statistical modeling. And then combining alerts or chemical fragments found to be significant by QSR models and prediction from statistical models and interpretation of statistical models as a way of both supplying statistically valid prediction and interpretation of this prediction in the form of significant alerts. So I'll talk to you about sort of hybrid methods that rely on this type of analysis. Sort of to summarize the strategy, what we'll talk about is how to integrate the data that have been historically used in cheminformatics type of analysis, making predictions of the ultimate in vivo toxicity solely from chemical predictions, but also how we could integrate the new type of data resulting from short-term biological assays, and how we could improve toxicity prediction using what I call here chemical biological modeling, also mindful of how we could build statistical models and interpret these models to improve both the accuracy of prediction and mechanistic interpretation. And so the three types of models that one could consider, I call them here hybrid models by pooling data, ensemble models from pooling models, and chemical biological read-across, which is a technique that we invented and introduced about a decade ago that we thought would provide the best way of integrating chemical and biological data. So hybrid model is very simple. We have chemical structures from which we could calculate chemical descriptors. We have biological assays, and we could integrate these types of features together, create a pooled data matrix, and create a hybrid model. Ensemble model is even simpler. We build models separately to predict in vivo toxicity from chemical structures, as well as predict toxicity from biological assays. And then I'll talk about CBRA, chemical biological read-across, that integrates chemical features and biological assays in a special way at the level of pulling together subsets of descriptors for compounds similar to the molecule in question to improve the prediction accuracy. So hybrid modeling, I'll allude to it very quickly because it's indeed very simple. In traditional QSR modeling, we just calculate chemical descriptors and use various machine learning techniques to predict toxicity. We essentially use the same framework applied to bioassay data. And if you concatenate chemical descriptors and bioassay data and still use the same modeling framework, you could potentially enrich and improve model accuracy through this simple integration of chemical and biological data. Want to talk more about it? We've published a lot of papers suggesting this different types of integration, demonstrating that generally, in most cases, you could improve model accuracy in predicting in vivo effects by integrating chemical and biological descriptors, typically by concatenating them. But in one case, we've we ran into a problem. And the problem was that when we tried to integrate chemical and biological descriptors in the traditional way, we've achieved models that were less accurate than by using just bioactivity data. And the specific problem at hand and challenge in hand was prediction of hepatotoxicity using either chemical descriptors or chemical genomics profiles. And so the experiments that have been done by a consortium of Japanese companies some years back was to expose animals to low, medium, or high doses of particular chemical at different time points, collect gene expression profiles as a proxy for short-term toxicity, and then sacrifice animals 28 days later and evaluate the hepatotoxicity, so-called subchronic assays based on histopathology of the liver assigned by trained pathologists. So that was the data set, and the objective was to predict hepatotoxicity, 28-day hepatotoxicity, either from chemical structures alone or from gene expression profiles collected after 24 hours following the chemical exposure, with some parsing of the data, progressively reducing the type, the number of genes used based on their relative significance, these gene expression profiles, and then compare also with hybrid models that would utilize chemical and biological descriptors jointly. And what we found was that purely toxicogenomic profiles were showing high accuracy of prediction, up to 78% accuracy. That was better than QSAR and better than even hybrid models. And so this sort of created a challenge and made us think deeper about the nature of integration of chemical and biological descriptors as applied to prediction of toxicity or any specific in vivo effects. And so what we thought of is what really happens when we do statistical modeling of a target property using features that characterize chemicals. In the chemical space, these features are based on chemical structure, and so we calculate chemical descriptors, and the values of chemical descriptors define the nearest neighborhood of each chemical in terms of chemical similarity. In biological space, we take measured biological features, we take measured biological responses in multiple assays, and the matrix, as I showed a few slides before, the matrix of data looks really similar to the matrix of chemical descriptor data. And so what we've realized by examining the neighborhood of each molecule in chemical and or biological space is that for the same chemical, there is different density of nearest neighbors, as you could see, in chemical space versus biological space. And frequently, there's also different annotation of those neighbors based on their toxicity assessment. And so basically what this tells us, and mind you that when we build QSR models or statistical models, those typically reflect the accuracy of models reflect the fact that similar compounds are expected to have similar properties. As you probably know, when this relationship between chemical similarity and biological similarity is violated, we have multiple artifacts. The best known artifact of the sort is activity cliffs, when similar chemicals have drastically different types of activity. And so in this case, as you could see, the environment of each chemical is different. And you should expect different accuracy of prediction. For instance, for this chemical, biological neighbors are distant. Chemical neighbors are close. So you should expect that more accurate prediction of toxicity would be based on chemical descriptors. And in this case, it's the other way around. For caffeine, it's the other way around. And so reflecting this aspect, we came up with a method that we call CBRA, chemical biological read across, which is learn from both sets of neighbors at once. So it's a k nearest neighbor method that is based on simultaneous calculation and scaling of both chemical and biological descriptors, and then looking at nearest neighbors of each chemical simultaneously, both in biological space and chemical space, basically identifying nearest chemical neighbors, nearest biological neighbors, and then deducing the toxicity of a chemical at question by weighted similarity assessment of nearest neighbors and the annotations as toxic and non-toxic. And so in carbamazepine, biological neighbors are distant. It would be wrongly predicted as toxic. It would be rightly predicted as non-toxic by chemical neighbors. And when we integrate, actually also overall correctly predict this chemical as non-toxic, because close chemical neighbors have great effect on toxicity. So this slide I could show briefly, basically the formula for calculating this weighted similarity is on top. And it shows, this slide shows sort of two aspects, quantitative prediction as well as transparency, because you could see how nearest neighbors of each chemical can be identified in both chemical and biological space. And so toxicologists who are interested in the argument behind claiming that a certain compound is toxic or non-toxic is based on nearest neighbors, and you could analyze their chemical structure and see it. So the method is also transparent, and statistically it showed the highest value of predictive accuracy. As a side note, we later realized that a similar approach could be employed when we have multiple chemical descriptors, and it's always an issue as to whether you build standard QSR models. There's always an issue as to how to choose descriptors. So this methodology that we call MUDRA, multi-descriptor read across, allows you to integrate multiple chemical descriptors and produce models and using diverse chemical descriptors, diverse types, similar to CBRA. So talking about ways of integrating statistical and non-statistical modeling, another methodology I want to introduce briefly, it's called chemistry-wide association studies, and it's based on GWAS approach, borrowed from genome-wide association studies, where we identify initially significant SNPs, and then look at co-occurring SNPs, and then examine gene-gene interactions associated with phenotypes. And so we decided to try to borrow the same techniques to create what we called CWAS, chemistry-wide association studies, and that deals with examining QSR models, identifying statistically significant fragments, looking at co-occurrence of significant fragments in chemical structures, and then employing pretty much the same methodology that was reserved for CWAS, fragment-fragment interaction, to extract synergy and antagonism between fragments. So this is how significant fragments are identified. It's pretty standard QSR model interpretation. And this plot shows how we identify co-occurrent fragments, and to illustrate, focusing on one of the fragments, nitro group, it's associated with mutagenic effect of chemicals in 84%, but if it co-occurs with another fragment that by itself is associated with mutagenicity 94% of the time, then the combination of these fragments make the molecule 100% mutagenic, whereas combining this chemical fragment with another chemical fragment leads to reduced mutagenicity. This slide also illustrates the weakness of chemical alerts, because as you could see, a single alert is associated with mutagenic potential not 100% of the time, and you need to, depending on what it's combined with, the compound would be 100% mutagenic or may not be mutagenic. And so to finish sort of the explanation of this paradigm, with chemical structural data, we do QSR models, identify significant fragments, identify mutually influencing fragments, and eventually combine QSR and fragments in a single workflow that is both interpretable and affords statistically significant toxicity predictions. So let me talk briefly in the last few minutes about the emergence and danger of sort of blind identification and the use of super popular hyped algorithms such as AI and deep learning. And as you could see, it was a lot of initial hype about the use of these methods when they emerged, although there were some observations that we need to be objective when we evaluate the results of these methods. And so one of the most famous stories 5 years ago was about a study looking at machine learning of big data in toxicity, and a method called RAZOR was developed, highly publicized, highly recognized, with social and scientific media glorifying this approach with very loud titles. So we've talked yesterday about the hype of AI. So that's a prime example of hype, as you see here. AI outperforms repetitive animal tests, etc. And the statistical accuracy of those models seem to have been very high. However, when we analyzed the results of this, what we had found was a lot of problems that dealt with a very, very simple issue of taking into account the accuracy of the data and rigor of modeling. So data that was used in the model were heterogeneous, inadequate, they were not curated, and finally, they were also data used from the ECHO database that were associated with predictions as opposed to measurements. So essentially, lack of data curation was the major observation and sort of weakness of this. And when data is not curated, when you have duplicates of the training set data in the external set, the model shows is expected to show over-optimistic accuracy. And so just to kind of alert you to how you should analyze publications that use most innovative methods, it's really important to look at the data carefully and see if statements made in the paper are really justified by the data. And just to illustrate that that's a broad scale problem, here is one of the early deep learning methods used in cheminformatics with a statement that deep learning methods significantly outperform all competing methods. But if you look at the data, with deep learning being the first column and random forest being the last column, as you could see, the largest performance difference between deep learning and SVM or random forest using the same descriptors was 0.04, with a standard error being a magnitude larger. So essentially, these methods did not provide any improvement. And again, we really need to be very smart and careful in evaluating what we do. And keep studying, and that's my last a few slides, on the importance of data curation and the importance of rigor in model development. So this slide talks about how one would curate the data. There are publications from our and other groups that talk about how chemical curation and biological data curation should be accomplished. So all the references are provided. Models, even in the age of deep learning, needs to be built with proper division of the data set into training, test, and external validation set. So all the best practices need to be preserved. And just to illustrate what happens when we build models, in this case, we're talking about a prediction of acute toxicity shown on the slide. And one aspect that I want to highlight is the importance of data curation. As you could see, curation of the data reduces the data set quite dramatically because of the presence of inconsistencies, duplicates, etc. So in one most dramatic case, the size of the data is reduced from 11,000 to 1,000, and that's pretty dramatic. But what's also important is that after the data curation, the model accuracy really drops compared to uncurated data. But this model accuracy is much more realistic, and it reflects the sort of innate inaccuracy of the data, perhaps, but it also shows the fair, the honest assessment of model accuracy using curated data and rigorous protocols for model building and validation that I absolutely encourage you to use in your work. So we talked yesterday about hype of AI. I mentioned the importance of overcoming hype in today's world. So I recommend you read this paper from Gartner.com. About hype cycle for AI, this is sort of my assessment that where we are with computational toxicology. As I mentioned in the beginning of the talk, the times are exciting. The amount of data is huge and growing. The importance of building reliable models of computational toxicity prediction was never as high as it is now. And with the overall trend toward elimination of animal models, will be greater and greater reliance on the use of computational methods in toxicity prediction. And so intelligent applications where we are, I think we're likely in the beginning of the plateau of productivity, and that's what we really need to focus on. So I think I don't need to read this. I talked about the importance of model accuracy, and the challenge is how to properly integrate short-term assay and computational data modeling to achieve models of the highest accuracy and minimize eventually animal-based toxicity assessment. So want to thank my collaborators, funding sources, and thank you for attention.